Now let's discuss how you connect devices up to the computer. So there are two main ways to connect devices, and that's using buses or serial links. So buses are parallel, that is, they have many bits at once. So you have 32 wires, for example, and you can send 32 bits together in one clock signal. Serial links, on the other hand, send one bit at a time. They're serial. So if I want to send 32 bits, I need 32 clock cycles to send 32 bits. Buses used to be everywhere. In fact, until about 10 years ago, everything was designed with buses. Links used to only be used where distances were long. So networks used serial links because they were long distances. But what we're seeing today is that while buses are still used inside chips, serial links are now used for almost everything else. And we're going to discuss why it is that serial links are better than buses today and how this is changing in the future. So first of all, what is a bus and how are they used? So if we have a CPU and we have memory and we want to talk to each other, what we're going to do is we're going to have a memory bus. And so this is a bus that sends addresses and data back and forth between the CPU and the main memory. So we connect the CPU and the main memory to it. Now if we also have some I/O controller, here we're talking to some hard disks or something talking to a network, we also want to be able to talk to that from the CPU. So for that we're going to have a special I/O bus that these use to connect, and then we need some sort of an adapter or a bridge that communicates between the CPU bus and the I/O bus. So what are buses? Well, they're a shared communications medium. So as we see here on the CPU memory bus, we have three devices that are all on the bus. So all the wires for the address and the data and control are wired up to the CPU, the bus adapter, and the main memory. When we talk about controlling the bus, we can have one master, that is one device that controls who has access to the bus. For example, maybe the CPU controls who has access to the bus. Or you can arbitrate among multiple devices. So the CPU can ask, does anybody else want the bus? And if they say no, it gets it. And then maybe the bus adapter can say it wants the bus if it has data from the I/O. Now how does a bus generally work? Well, whoever's the master puts an address and a command on the bus. So the CPU says, I want to write to address 128. The slave, that is the device that's going to respond to this, receives the address and the command and prepares to get the data if it's doing a write, or send data if it's doing a read. So here the main memory knows that that's its address, or that that address corresponds to it, so it prepares to receive data. The next cycles, the master is going to put data onto the bus, and the slave will store it. So here the CPU can put some data on the bus, and the main memory knows that it's expected to write the data, so it gets the data and knows which address to write it to. If we're doing a read, it would be the other way around, where the CPU would wait for data from the main memory. So what is a bus physically? Well, it's just a lot of wires. So here's our processor and our memory, and we're going to have wires for the address, and wires for the data, and wires for the control. So if we have wires for the address, maybe we have 8 of those, 8 wires for the data, and a bunch of wires for control. Here we have a wire for reading, a wire for writing, and a wire for the clock. When we want to send data, we're going to need to set up the data on the wires and send the control and the clock signal. So to send this data, we just go and set the wires to do what we want, and the device gets the data. Now you'll notice here the device is also getting the clock signal, so it knows to write the data to the address on the clock. So the example we have here, we have separate data and address buses. In the previous example, we had one bus that we used some of the time for data and some of the time for address. And which way you decide to design something depends on whether you want to have more wires or fewer wires. So what's the big problem with buses? Well, what happens if signals are late? So I want to go ahead and send this data, but this time some of my wires take longer than others. So I go ahead and start sending the data, but it doesn't all get there at the same time. So here's the data I wanted to get, but when the clock edge rose, so when the clock became 1, here was the data I actually had. So I'm going to go ahead and write the data to the address when the clock rose, but I didn't get all the right data. So now because some of those wires were slow, I've corrupted my data. The only way to handle this is to slow down my clock speed so all the data gets there in time. So what's the problem with buses? Well, it's basically that the wires are ugly. And they're more so as things get smaller. So as we have smaller and smaller wires and want to run faster and faster, wires get harder and harder to manage. And the reason for this is that wires have capacitance, inductance, and resistance. They're complex circuits. And this makes them slow. And particularly with buses, if we have multiple things on the bus, each one of those things on the bus adds more capacitance, more inductance, and more resistance, and slows down the wires. Wires also interfere with their neighbors. If I have a wire next to me that has a 1 on it and I have a 0 on it, that 1 is going to try and pull on my 0 when it changes. So you get noise from your neighbors. So the real problem with buses is it's very hard to keep wires synchronized to the same clock. So if I want to have 32 wires to have a 32-bit bus, I need to make sure they're all synchronized to the same clock. And this is difficult. Let's take a look at an example of that. So here's a circuit board from a graphics processor, and you can see all the traces on it. These are wires coming out from the processor. Now if you look at the side here, you see an awful lot of very squiggly wires. And the question is, why did they make these wires be so squiggly? They could have just run them directly. And the reason is they're trying to make all the wires the same length. So by adding these extra squiggles, they're trying to equalize the wires so that the data on the wires all get to the destination at the same time. Now it's not just the lengths of the wires that's a problem. If you look at all these holes, these are vias. Each time a wire goes through a circuit board, it adds capacitance and inductance to the wire and slows down the wire. So you need to balance the length, you need to balance the number of vias you have, and a whole bunch of other things to make sure you can run your wires quickly. Alternative to running buses, which is lots of wires in parallel, is to do serial communications. And in serial communications, you send 1 bit at a time. Now, if you're sending 1 bit at a time, you have to figure out when those bits start, so you need to figure out what the clock is, because we're not sending a clock the way we did with the bus. Serial communications is also point-to-point. That is, it's not shared. So if we want to communicate with 2 different devices, we need 2 different serial communication links. But we can run much faster than buses, and the reason is we don't have to synchronize with all the wires. We don't have to worry about making sure all of our wires match up. The downsides of serial communications is much more complicated. As we mentioned, we have to figure out where the clock is, and we can do a whole bunch of other tricks to run much faster, including calibrating the wires and equalizing them. And serial communications are used wherever wires are long. And long is a definition that changes, because the faster you want to run your data, the longer a wire seems. So if you're doing very slow communications, you can use a very long wire. If you're doing very fast communications, you have to keep your wires short. So let's take a look at sending some serial data. Here I'm going to send the same data I had before, but I don't have a clock and I only have 1 wire, so I'm going to have to send 1 bit after each other. So you can see I send the control data first, then the address, then the data. So how are we going to actually transmit this? Well, we're going to transmit it in order. So the first bit's first and the last bit's last. And what is this going to look like? Well, we're going to have a signal that goes up and down over time. So instead of sending all of these bits at once, we're now sending them one after another. However, to understand this, we need to figure out the clock and figure out where to look. So the receiver has to know that these are where the bits are, so that it can look at that signal and get the data at the right time. And this is a tricky thing to do that we're not going to talk about in this class, but people know how to make this work. So serial communications can do something very clever to reject noise. So if we can use 2 wires and make the links much better, and the way we do that is by having 1 wire send our signal, transmit plus, and the other send the negative version of the signal, so transmit minus. At the end, we're going to subtract them to get back the original signal. And let's see why we do that. So here's our system. Here's the signal we want to send. So what we do is we send 2 versions of it, the negative version and the positive version. And then at the other end, we subtract them to get the data back. So why is this beneficial? Well, if there's an electrical noise in the middle, that noise is going to affect both wires. So here you can see that this red noise makes both of them go more positive, but when I subtract out the results, I also subtract out the noise. So why is this approach better? Well, it's better because when we subtract, we remove the noise. We have 2 wires, and if they're close together, whatever noise is coming from outside will affect them both the same way. When we subtract them, we get rid of that noise, and that gives us a stronger signal, which means we can make our data go faster. So let's take a look at how differential signaling works. So we're going to transmit 2 versions of our signal, plus and minus. And so here's the minus version. We've just multiplied everything by -1. Now I've got 0 minus 1, 0 minus 1 instead of 0, 1. This is an analog signal, so it's not really a digital signal. So we don't have to just have 0 and 1, we can use different voltages. At the end, we're going to subtract this, so now we go ahead and we create our signal and transmit it. Now let's take a look at what happens when we do the subtraction. So when we subtract them, we get back the original signal. In this case, we're going to get 0, 2, 0, 2, 0, 2, 2, because we're doing 1 minus -1, which is going to give us 2. So now we have our original signal. Now let's see what happens when we add noise to the signal. So say we have this noise spike in the middle of our signal. What does that do to our signals? Well, you can see how it's affecting both the transmit plus and the transmit minus. It's moving them up by half. How does this affect our final output? Well, if we look at what's happening here, it doesn't change anything. Because at this point here, instead of having 0 minus 0 to give us 0, we now have half minus a half, which still gives us 0. We've subtracted out that half that came from the noise. And the same thing happens here. Instead of having 1 minus -1 to give us 2, we get 1.5 minus -0.5, which also gives us 2. So by using the differential signals, we can take noise that affects both wires and subtract it out. And that gives us a cleaner signal, which allows us to run much faster. So what sort of I/O interfaces do we have today? Well, here's a layout for a modern processor chipset. And we can see that when we talk between the processor and the rest of the computer, we're using QPI if you're Intel or HyperTransport if you're AMD, and these are both point-to-point serial links. We have PCIe for talking to graphics cards, and this is again a point-to-point serial link. We have other connections such as SATA, which is also a point-to-point serial link. And then we have I/O connections for external devices such as USB and Ethernet, and USB is serial link, and Ethernet is also serial link, but they're not quite point-to-point. The memory is still sitting on a bus, but it's very limited. Usually we can only put 2 things on this bus because we don't want to slow it down too much. So, to sum up buses versus point-to-point serial links. Off-chip buses are going away because they're too slow. You've seen PCI go to PCIe, ATA go to serial ATA, etc. Why are they doing this? Well, data is too fast for long wires. The wire has capacitance, and because it has capacitance, it takes a long time to change the voltage. The longer the wire, the greater the capacitance, the longer it takes to change. It's also too hard to handle multiple devices on the same wire. So when you have multiple devices, you get more inductance, more capacitance, more resistance, and each additional device slows down the wires. And the real reason it's too hard to keep wires synchronized. Both of these other 2 issues, with wires being too long and wires being complex, means it's hard to keep the data in sync. And if we can't keep the data in sync, then we have to slow down the clock speed, and then the bus is slower. So the replacement, as we talked about, is serial communication, or SERDES. This stands for serial deserialization, and the idea here is we send 1 bit at a time. So there's no need to synchronize the wires because we're only sending 1 bit at a time. We figure out the clock as part of the signal. This is well known how to do, although it is tricky. But we do need to run much faster to get the same throughput. So if we're replacing a 32-bit bus with 32 wires with 1 serial link, that serial link has to run 32 times faster to send as much data. So the reason we can do this is because while they're more complex, we can afford the transistors. So we can afford to spend a lot of transistors to make a clever serial port instead of trying to figure out how to make a better wire. So we've said that off-chip buses are going away, and we're going to see the same thing in on-chip buses in the future. So when we start seeing 100 cores on a chip, we're also going to start seeing serial links on chips. The other thing that's important to keep in mind here, that while these transistors may be free, they also use a lot of power. So these serial ports use a lot of power on chips. So that part is not free. So a question, what is the main problem with buses today? Well, the main problem is it's hard to synchronize lots of wires. We can build lots of wires, it just takes space, but keeping them all in sync is hard because they have different capacitance and inductance. If having a problem with shared wires is they make the synchronization even harder because they add more capacitance and inductance to the bus. So how can we have 2 PCIe devices in a computer if PCIe devices use point-to-point links and not a shared bus? Well, the answer here is we have to have multiple PCIe links and we have to divide them up. So the links in PCIe are serial, so they can only go to one device. If we want to have multiple devices, we have to divide up the links between the devices. This means that none of the devices can get the full bandwidth because they have to share it.